All right, thank you, Gina, and thank you to the organizers for letting me kick off this exciting session today on the interstellar medium. So I'm going to be talking about mapping galactic magnetic fields with interstellar dust, and there's certainly far too much to this topic to do justice to it in 20 minutes. So I've definitely done a lot of picking and choosing, so you'll have to forgive me if I've done some overcondensation. And I've also decided to focus explicitly on dust polarization. Um, synchrotron polarization is, of course, important. I think we'll be hearing about it a little bit in the session today, but just not enough time to go into everything that I would ideally like to. But my one little homage to synchrotron polarization is the image here on my first slide, which is showing magnetic field lines in the galactic center as observed by the Atacama Cosmology Telescope. And so these are primarily from synchrotron emission, but also from dust. So what I'm hoping to do in this talk today is to give a little bit of an overview of both kind of where we've been with understanding magnetic fields using dust polarization, and then a bit of looking forward to where we're going with efforts that are currently underway. So let me start at the beginning and say that the polarization of starlight by dust grains was discovered serendipitously in the late 1940s by Hiltner and Hall independently. And it was immediately obvious that this polarization must be arising from the interstellar medium because one, there was an observed large-scale coherence, which you can see in the figure here, which comes from just plotting polarization vectors from the Hylas catalogs, and actually a lot more stars than were available to Hall and Hiltner. So large-scale coherence, so you wouldn't expect that if the polarization were local to the stars, and then also the level of polarization was highly correlated with the interstellar reddening. So, it was pretty much immediately realized that this polarization must be coming from interstellar dust grains. And so the way that this works is that the aspherical dust grains, so you can imagine a little football shape like I have here, are systematically aligned in the interstellar medium with the local magnetic field. And their short axes are aligned along field lines. And so that means the starlight polarization is polarized in the parallel to the magnetic field orientation. And so the first theory of grain alignment was articulated very shortly after the first observations of starlight polarization by Davis and Greenstein, and also Spitzer and Tukey. Our understanding of grain alignment has evolved quite significantly since the 1950s. I will not go into that right now, but it sounds like BG will be giving us a talk later today on grain alignment, so looking forward to that. So this means that we can use these observations of starlight polarization to map the magnetic fields in our galaxy. So in a little bit more of a preview of things to come today, here's an example of that from the recent GPIPS collaboration paper, Clemens et al. How we can take these measurements of polarization angles to individual stars and build up a picture of what the galactic magnetic fields must be doing. And I thought this image was just really incredible in the dynamic range covered, going from very, very small angular scales to very, very large ones. And this is a very nice demonstration of the ability of starlight polarization to be able to trace the morphology of the galactic magnetic field. But we can actually do even better than that with starlight polarization in terms of, not just the field orientation, but the field orientation in 3 dimensions. And so there's a really interesting little tidbit from this paper from Hiltner 1951, where he's noticed that there's these 2 stars that are really close together on the sky, just less than an arc minute apart, but the polarization angles are different by about 8 degrees. And so what he suggests is going on here is that the stars are not co-located along the line of sight, but rather one of the stars is being polarized by dust that is aligned by one magnetic field, the nearest star. And then the further away star, there's extra dust in between it and the nearer star that's aligned with a different magnetic field orientation, such that it causes the polarization angle to rotate. And he notes at the very end that in order to be able to test this at any level of detail, you needed to wait until the spectroscopic parallaxes become available. Well, now here in the 2020s, this is actually very feasible now that we have Gaia. and know the distances to all of these stars. So this is a very nice work from Gina from a couple of years ago, using Robopol polarimetry of stars in a well-defined region of sky, where each of these stars we have a distance. And so you can look at the level of polarization and the angle of polarization and how that varies with distance. Now, just looking at this plot and not being able to do any statistics by eye on it, everything seems fairly consistent with a single polarization level and a single orientation. But if you actually dig into the data and construct a model, what you realize is that what you're seeing here is not just simply a single uniform magnetic field, but rather you're seeing a transition between stars that are polarized by essentially one dust cloud, and then stars that are being polarized by two dust clouds at a further distance. And so if you work through the math of that and make a prediction based on those data of what those field orientations are, you end up saying that there's one cloud that has an orientation that looks like this, and another cloud that has an orientation for the wave cloud that looks like this. And if you superimpose these inferred polarization angles on H1 data, as is done in this paper, you see that you end up with something that's very coherent with the orientation of these H1 filaments. And so this is a really nice demonstration of the ability to not just to map magnetic field orientations with stellar polarizations, but to be able to do so in 3 dimensions. And so what the dream, of course, is, my dream and a lot of people on this call's dream, is to be able to combine starlight polarization with the Gaia distances to make a true 3D map of galactic magnetic fields, very much an analogy to the way that we have these new 3D dust extinction maps using the synergies between stellar distances and dust extinctions. So, why are we not there already? So there's some limitations, some of which will be addressed by more data and some which not. Is one, that there's not yet a sufficiently large stellar polarization survey to where that we can really do true tomography. So, in this one region that we just saw with the Robopol data, yes, we had enough stars to be able to do tomography, but that's one region of sky that's really been drilled down on. It'd be nice to have such data over large sky areas, which just don't exist yet. Another limitation of all this that I want to spend some time talking about is that in all of this, what one really gets is not the full 3D magnetic field orientation, but rather just the plane of sky component. So we need to do a little bit of extra thinking in terms of how to infer what that line of sight component of the magnetic field is to get a true 3D map of 3D magnetic field orientation. And then finally, I've talked exclusively so far just about magnetic field orientations. And that's because if you want to infer something about the field strength, one needs to be a little bit cleverer to apply some analysis to the data. It's not something that's probed directly. I think Raphael's going to be talking about that a bit in the next talk. Okay, so I've talked so far about starlight polarization and it as a powerful probe of magnetic field orientation, but it's not the only tool that we have in our toolkit. It's not the only way to do this, because those same grains that are aspherical and aligned that are absorbing starlight polarization re-radiate that energy in the far infrared. And that radiation is also going to be polarized, but this time perpendicular to the magnetic field lines, because that's associated with the long axis of the grains. And so this has been appreciated for a very long time. There's a nice paper from Stein in 1966 thinking about, wouldn't it be nice if we had something like a satellite making far infrared observations of dust polarization. And one of the virtues that he noted about this was that since the optical depths in the infrared are so small, you'd be able to see polarized radiation out to very, very large distances from the Earth. So it indeed has some advantages over the stellar polarization as a probe of magnetic field orientation. So, again, here in the 2020s, we now have this early dream realized. So this is a map I'm sure you've all seen before from the Planck satellite. So this is measuring polarized dust emission at 353 gigahertz, 850 microns. and usually smooth to a resolution of something like a degree, although in bright regions of the galactic plane, you can do something like 5 arc minutes. And here, the contour lines are showing the inferred magnetic field orientation. And so, in some sense, we have a nice full sky map of the uh, galactic magnetic field orientation as inferred from the polarized dust emission. And so with this, full sky view, that allows us to really put constraints on everything from, the global galactic magnetic field, but also the magnetic field immediately in the stellar neighborhood. Since, the amount of dust column that we're actually probing, particularly when we look at high latitude sight lines, we're probably looking at stuff that's at most a few hundred parsecs away from us. And there's been some great work on this from some speakers that we're going to hear about later in the session today. Although I don't think this topic necessarily specifically, so from Andrea Bracco and Rafael Skoulides and Vincent Pelgrims. So definitely read those papers and chat with them about it. But the limitation of the far infrared, so it's nice that we have this nice full sky view, but it's line of sight integrated. So you're seeing the full dust column. So you've lost all of that beautiful 3D information that was allowing us to do tomography with the stellar polarization data. It's also the case that, like starlight polarization, you're not getting a probe of the line of sight component of the magnetic field. You're only looking at the plane of sky. So if we want to do something better than that to probe the 3D field orientation, you have to be a little bit cleverer. One of the things that came out of the Planck analysis of the far infrared dust emission and polarization is just how tightly connected it is to the optical polarization, such that if you measure one, you can make a very good prediction of the other. That there seems to be these characteristic ratios that characterize the amount of optical polarization per amount of far infrared polarization. And this is just a demonstration of that in the Planck data using a sample of about 1,500 stars. And it's just beautiful linear relationship that pops out. And if one takes this to its logical conclusion, Planck sees dust polarization fractions that get up to about 20% at 850 microns. And if you propagate that to what one expects in optical polarization, you get these very, very large stellar polarizations that would be implied. So back in 1975, Sierkowski made a determination of kind of this upper envelope of stellar polarization. What is the maximum stellar polarization that you could get, per unit dust reddening, assuming that the magnetic field geometry was just completely ideal, perfectly in the plane of the sky. And he came up with this 9% number that this was the optimal geometry case. But if we take those Planck results at face value, we would say that Sierkowski has underestimated this envelope. And so to test this, what we did using Robopol was saying, okay, well, we can go to one of these regions where Planck measured this 20% polarization fraction and asking, do we see stars that are polarized in excess of this 9% envelope? And so this is a paper with Gina and other Robopol collaborators that we wrote in 2019. And indeed, we found that the stars were polarized well in excess of this classical 9% polarization per EBV envelope that is kind of held since Sierkowski 1975. And in fact, Planck suggested revising this envelope up to about 13%. And depending on what extinction map you use, you might even say it should be even a little bit higher than that. So it does seem that the intrinsic polarizing efficiency of dust grains in the optical has been underestimated for a very long time. And if one looks at these very special regions where we're seeing very high polarization fractions, of probably very ideal viewing geometry, uncomplicated line of sight, plane of sky magnetic fields, that really you can get polarization fractions up to this 13% per EBV. Okay, so there's a lot that could certainly be done with a combination of Starlight and far infrared. But I would say in some sense, Starlight is kind of the ultimate probe because it preserves that line of sight information. Unfortunately, we're really limited by the number of stars that we currently have with polarimetry. And one could imagine if we had a joint model, if we had stars over a large fraction of the sky, and then we have these far infrared observations that we know are highly correlated, we could really do a nice job of doing a joint model of what this 3D magnetic field geometry is over the full sky. And then finally, I want to note that the actual numerical correlation between the starlight and the FIR polarization is actually a very sensitive probe of the actual dust itself in terms of both its shape and its composition. So this is a paper that Bruce Drain and I wrote just this year, where we argue that these characteristic ratios favor preferentially oblate grain shapes, kind of with a 1.4 to 1 or 1.6 to 1 axial ratio. Okay, so what does the future look like? So I've made a lot of noise about we don't have enough stars, and the pacify experiment is hopefully going to take care of that problem. So this is a planned survey from Skenikos Observatory in Crete and the South African Astronomical Observatory in Sutherland. And the idea is to map millions of stars at high polarimetric accuracy with a particular emphasis of going all the way up to very diffuse sight lines and high galactic latitudes. And so we can combine these stars with the Gaia distances to do true 3D tomography. And of course, there's also strong synergies with the foreground mitigation for CMB polarization experiments, where they're wanting to model the dust and the magnetic fields in order to be able to subtract it out to get to their cosmology results. First light for pacify is actually anticipated later this year. And just to give you a quick idea of how big of a step forward this is going to be for this field, forecasting 1,000-fold improvement in the number of stars with polarimetry at high latitudes. Whereas now, we have much fewer than 1 star measured per square degree at high latitudes. And with something like pacify, we're talking about being able to measure hundreds of stars per square degree at high latitudes. Is truly going to be transformative. So in the last few minutes of this talk, I just want to highlight a few kind of outstanding questions and things to tackle with pacify and with other dust polarimetry that we can sort out. So I think this is just a personally curated collection of interesting, outstanding questions. So these are the PNS relations, 3D D-field orientation, relationship between dust and gas filaments, and 3D mapping with ices. So just diving in first to the PNS relations. By this, I mean the interrelations between the polarization fraction P, the column density N, and the polarization angle dispersion S. So by polarization angle dispersion, I just mean how much variation within a given region does the polarization angle have? Is it all very uniform and coherent? Or are the polarization angles kind of all over the place? And so these 3 things can inform us about the magnetic field disorder, but also has information on things like the line of sight orientation of the magnetic field, the thing that is not directly inferable from just measuring the polarization angle. Also things like loss of grain alignment. But I think there's still a lot to understand. What are the physics driving these relations that have now been measured in a number of environments, including the dust, including the diffuse interstellar medium, and including dense molecular clouds, to understand really what's causing the different slopes and even just different qualitative behavior in these relationships. And
2 more minutes, Brenda.
And I think it'd be particularly exciting to bring starlight polarization to bear on this problem as well. So just as a recent example from Sullivan et al. From this year, looking at the P versus NH relation in a number of clouds, and they find, and has been found much in the past, a tendency for the polarization fraction to decrease as the column density increases. And this has kind of been classically interpreted as you're adding dust emission as you go up in column density, but you're not adding dust polarization. So the dust grains are possibly not very well aligned deep in the dense regions of these clouds. So one explanation for this P versus N slope is a loss of grain alignment. This has also been looked at kind of in the diffuse medium, but also getting up to fairly high column densities in this Planck paper, where indeed they find this decline of the polarization fraction with the column density, But what they argue is this is actually perfectly offset by the increase in the polarization angle dispersion with column density. And their argument here is actually because the product of S and P is so constant, as you can see down here in this bottom panel, that really what might be going on is not that the grains are no longer able to be aligned, it's just that magnetic fields are getting more tangly as you get to higher column densities. So you're just seeing the effects of depolarization rather than loss of alignment. So I think that there's outstanding questions and things to be dug into here. The other thing that is embedded in this is the 3D field orientation. It's thought that some of these relations are dependent on the orientation between the magnetic field and the line of sight. So just to give a quick picture, if you have an aspherical grain and you're kind of looking down the barrel of a magnetic field like this, small perturbations to the magnetic field are going to cause big perturbations to your polarization angle and give you lots of polarization angle dispersion. So in this instance, you would have a high S. And then also, if your magnetic field is parallel to the plane of the sky, and you wiggle it around with some turbulence or whatever, then you get very little change in your polarization angle in projection. And so this would be associated with regions of low S. We can actually use polarization angle dispersion as a probe of line of sight orientation. As also illustrated in this diagram, the actual grain cross-section also changes as you step through these scenarios, such that the grain cross-section is larger here than it is here. So you actually expect the total intensity from the dust to be higher here than in here, that to be dependent on orientation. And so we actually detected this in data. So this is work done with Caltech PhD student Cheng Zhang, where we looked at the dust emission per H1 as a function of S, which is our proxy for line of sight orientation, and indeed found that when the magnetic field is in the plane of the sky preferentially, we see lower dust intensity per H atom than when the field is mostly line of sight, which is kind of exactly the prediction from this picture. So this is an effect that has been now detected with Planck data in far infrared polarization. It'd be very interesting to see if this could also be detected using Starlight polarization data, because it should be in extinction as well. Okay, and then last two things, just very quickly, one slide each. We know that H1 filaments are able to trace starlight polarization and polarized dust emission just by looking at the way these little H1 filaments are oriented. You can do a good job at predicting the polarization angle. This is the work of Susan Clark and collaborators. I've also been involved, and Vincent is going to talk a little bit about this in his talk. And so you can see the polarization angle represented in textures from the H1 on top, from Planck dust emission in the bottom, and then the polarization from stars in the little line segments, and all three of those agree very well. There's some indication that this doesn't work very well on very small angular scales, but we currently don't have the data to test that. So you need either better infrared data or more stars. And then last thing I promise is to think about ice polarization. And this is, I think, an interesting observational window that hasn't really been exploited very well. That we get these ice spectral features in the dust extinction, that they can only live in very dense environments deep within clouds. So if you measure them in polarization, you know that you're detecting magnetic fields that are deep in the cloud and not just dominated by what's going on at the surface. This has been done for Elias 16, as pointed out by Doug Whittet, but to date, it's really the only star that this has ever been done with, and I'm not aware of a capable instrument that could do this kind of spectropolarimetry at these mid-infrared wavelengths. And I think I'll just leave the summary up there to take any quick questions. And so thank you much for your attention, and sorry for covering so much in so little time.